Hello, my name is André. I'm from the Universidade Federal do Paraná in Brazil, and I thank the organizers for the opportunity of participating on the session of recent progress in nonlinear PDEs and their applications of the Mathematical Congress of the Americas. This is a joint work with Professor Francisco Guilhem Gonzalez from the Universidad de Sevilla in Spain. The title of the work is A Regularization for a Chemo-attraction Model with Consumption. So I begin by talking about chemotaxis and chemoattraction. Chemotaxis is the movement of cells in response to the concentration gradient of a chemical substance. And the cells can be attracted or repelled by the greater concentration of this chemical substance. If the cells are attracted, then we say we have chemoattraction. And if the cells are repelled, then we call it chemorepulsion. Chemotaxis is present in many biological processes, such as the immune cells migration, the migration of bacteria towards polluting substances, cancer growth, among other interesting applications which make of chemotaxis a matter of very practical interest. One of the first models has been proposed by Keller and Segal in 1970. And since then, many researchers have been studying this and other related models. One model related to the Keller-Segal model is this chemo-attraction model with consumption. Let omega be a bounded domain in Rd, d being the dimension of the space, which can be 1, 2, or 3. Let 0t be a time interval. Then we consider these two real functions defined on this Cartesian product. U is the density of the population of cells, and V is the concentration of the chemical substance. The chemo-attraction model with consumption is governed by these equations. So we have the meaning of some terms here. We have the terms related to the diffusion effect, and we have the term related to the phenomenon of chemotaxis, and we have the consumption term too. The consumption term has an exponent s, which we consider to be greater than or equal to 1. And we also have the Neumann homogeneous boundary conditions and the initial conditions completing the system. And what do we know about this chemo-attraction model? So there are some studies, some theoretical studies, if we consider the exponent s equal to 1. Then we have existence of global weak solutions in 3D and existence and uniqueness of a global classical solution in 2D in smooth convex domains. We have existence of global classical solutions and 3D smooth domains with a smallness condition on the initial data of the concentration of the chemical substance. And we also have the chemo-attraction model related to coupled with fluids. So in this setting, we have existence of global weak solutions in 3D and existence and uniqueness of global classical solutions in 2D, considering the chemo-attraction model coupled with fluids and in smooth and convex domains. And then we have the extension of this work to smooth non-convex domains. So these are the theoretical studies. And concerning the numerical approximation, we know the following studies, also for the exponent s equal to 1. So concerning the numerical approximation, we have a study which deals with the numerical approximation of sufficiently regular solutions of the chemo-attraction model with consumption coupled with fluids. And we have a study dealing with the numerical approximation of solutions of the chemo-attraction model with consumption without fluids. This one has the participation of Professor Francisco, and it has been submitted but not published yet. So we realized that there are few studies on the numerical approximation of the chemo-attraction model with consumption. So in order to contribute with this theme, I show you the contributions of this present work. So our main objective was this first contribution. We introduced and analyzed regularized models, which will be useful for designing numerical schemes that will be used in order to approximate the original model in a forthcoming work. So we introduced regularized models that will be used for the numerical approximation of the original model. This will be done on a forthcoming work. And comparing to the literature, as a byproduct of our analysis, we also generalized the model, considering a more general consumption term with S not only equal to 1, but S also greater than 1. And we also enlarged the class of considered domains, including non-smooth and non-convex domains, for example, C2-1 domains. Okay, so once we talked about the contributions of this work, I'm gonna talk about the regularized models. In order to introduce the regularized models, we must define this truncation of the identity function. So for each m, each natural number m, we consider the following truncation, which we denote by am. And once we defined the truncation am, we can define the regularized models. So for each m, we will consider the truncation am in the chemotaxis term and in the consumption term. So this is the way that we obtain the regularized models. And the boundary conditions and the initial conditions remain the same. Okay. The idea is that when I make m go to infinity, these solutions um and vm of the regularized models will approximate a solution of the original model. Okay, so this regularized model is intended to be a kind of approximation of the original model. Okay, but before proving these approximation of this convergence as m goes to infinity, we have to study this regularized model. The good news is that this regularized model is easier to study, and we can do it via Galerkin's method. Okay, so here we consider omega to be a C2-1 domain or a polygonal domain in R2. These polygonal domains of R2 are interesting from the applications point of view. We also suppose U0 and V0 are H2 functions, and we define this average of the initial condition U0. Okay. Then for each m, we can use Galerkin's method in order to study the regularized models. And we can prove the existence and uniqueness of a strong solution VM with this regularity. And the regularity holds up to infinite time. Okay. And we can also study other interesting properties, such as the positivity of the functions um and vm. So if we choose initial conditions, non-negative initial conditions, okay, so U0 greater than 0, and here if we take this alpha to be greater than 0, then we'll be considering V0 greater than 0. We can prove the positivity of U and V, and also if the initial condition is bounded, if the initial condition of the chemical substance concentration is bounded, then the solution Vm is also bounded. Okay, and we also have these m-independent estimates for um and vm. Here I remark that these properties, as well as the existence, uniqueness, and regularity results, are important for that forthcoming work that I mentioned before on the numerical approximation of the chemo-attraction model with consumption. Okay, and then you remember that I told you that we want to take the limit as m goes to infinity. We want to make m go to infinity and show that UM and VM maybe up to a subsequence will converge to a solution of the original model. So in order to do it, if we want to prove the convergence of UM, VM towards a solution of the original model, we must obtain m independent estimates for UM and VM. And with this purpose, we base ourselves on a formal energy identity that we can obtain for the original model. Okay, so this is the formal energy identity. And we have a function g here, which is a primitive of this function g prime, depending on the exponent s. On the left-hand side of this equation, we have terms which have a good sign. They have a defined sign. But on the right-hand side, we have this term involving the Laplacian of v, which we are not sure about the sign of this term. We don't know if it's a source term or if it's a dissipative term. It does not have a defined sign. So we have to estimate this term. But you see that it has some derivatives. It has derivatives of second order. So it's difficult to conveniently estimate this term. So this will be the difficulty that we will find in this process of obtaining m-independent estimates for UM and VM. The treatment of this term is a challenge. So in order to conveniently estimate this term, we must prove a series of results, and then a restriction appears here. Okay, so in order to prove these results, we must assume these hypotheses. Okay, the hypothesis is the following: if v is an H2 function satisfying this boundary condition, then there's a sequence vk of C2 functions also satisfying the boundary condition, and such that the sequence vk converges to v in the norm of H2 as k goes to infinity. Okay, so it's a kind of density result. And it seems to be a very natural result, but we were able to prove only in the case where omega is a C21 domain. That is, in the case in which the boundary of omega is a C21 function. Okay, so here is where the restriction of omega being a C21 domain appears. If one can prove that other domains satisfy this hypothesis, then we can enlarge even more the class of domains that are considered in the work. Okay, but here is just to give you an idea of where this restriction appears. So once we estimate this term, considering C21 domains, we can estimate the aforementioned term, that involves the Laplacian of v, and we can obtain m independent estimates for the sequences UM and VM. And if we find these m independent estimates, we can use compactness results. So with this compactness results, we can conclude that there are subsequences that converge and the weak topology of some spaces and then the strong topology of other spaces. Okay, so using these compactness results, we can pass to the limit as m goes to infinity, and we can conclude that there exists a solution to the original model, u, v, okay, satisfying the original model. And this solution, uv, is obtained through the limit of solutions of the regularized models. It's obtained through the limit of um and vm, in other words. Okay, so this way we prove the main results of this work. So the main results are the existence of global weak solutions at finite time, considering t final time greater than 0, considering omega C21 bounded domain. Let U0 be an H1 function and V0 be an H2 function, both non-negative functions. Then there is a solution UV of the original model for s greater or equal to 1. And this solution is obtained through the limit of a subsequence of UMVM. And the solution of the original model UV has this regularity. Okay, so we can see that the regularity depends on the exponent s. And for the function u, and for the function v, the regularity does not depend on the exponent s. Okay, this is what we have in 3D. We have only existence. And in 2D, we have existence and uniqueness of global strong solution at infinite time. Okay, so with the same hypothesis of omega being a C21 bounded domain, now we consider U0 and V0 to be H2 functions, non-negative H2 functions. Then there's a unique solution UV for the original problem, and it has this regularity. And now the regularity of u and v are the same, and they don't depend on the exponent s. And in particular, u is a bounded function, and we can prove that we don't have to make m go to infinity in order to obtain the solution of the original model through the limit of solutions of the regularized models. Okay, there's a sufficiently large natural number n0 such that for m greater than n0, the solution of the regularized model and the solution of the original model are the same. Okay. And then concluding, for future research, we intend to propose and analyze numerical schemes in order to approximate the solutions of the regularized models. Then we will study the convergence of these numerical schemes towards the original model in terms of the discretization and regularization parameters. Okay, and then after, we intend to perform numerical simulations in order to verify the theoretical results and compare the performance of the different proposed schemes. Before finishing, I'd like to thank my advisor, Professor Pedro Damasio, for his guidance and fruitful discussions. And I'd like to acknowledge that this study was financed in part by the Coordenação de Aperfeiçoamento de Pessoal de Nível Superior, Brasil, CAPES. Here I present you the references that I mentioned before, if you want to consult it. Okay, so thank you for your attention.